Hello. We'll talk today about free Bessel laws and quantum algebraic aspects of them. So these free Bessel laws, we already met them in the previous lecture. These are compound free Poisson laws of a very simple type. And the idea is that they have a very, very interesting structure. I mean, both probabilistically and they are related to quantum groups, things like that, also some factors. Noncommutative geometry, they are somewhat at the core of the various branches of quantum algebra. It's the common ground somehow. And then you have to understand first, and then the idea is to build on that. So that's the plan for today. We'll try to understand this central thing. And let's find this presentation. Here we are, so quantum algebra, free Bessel laws. What's the plan? Well, we'll first talk about quantum groups. So remember last time we had these cubic diagrams, every single partitions and all that. And the quantum group viewpoint on that is the best. So first talk about quantum groups, general theory. Then we'll do Weingarten integration in continuation with what we did in lecture 1. There it was Weingarten for usual groups, rather lecture 2. In lecture 2. So we'll generalize all that in the quantum group setting and compute laws of characters and have this cube done in a very nice way. Now, once the cube done, we'll go back to the free Bessel laws and we'll have a discussion, a probabilistic discussion about them, very as advanced as we can. And then we'll discuss other quantum algebraic aspects of them, like in relations, factors, noncommutative geometry, other things. So let's have this started. So quantum groups, I remind you the end of the game. Where is it? So in the first lecture, we've seen that the interesting groups, the most interesting ones are O and UN, and also these reflection groups. And I have to liberate them in order to get as character laws the free analogs of the Gaussian and Poisson and Bessel laws. So the first slides here will be just general theory of quantum groups. It's not very complicated. So these things were discovered by Voronovich in the end of the 80s. So his formula is as follows. So let's take a sister algebra A, we call such things Voronovich algebras, with a unitary matrix, and by n whose entries generate A, such that, so you have a delta map, an epsilon map, and an S map given by these formulas here. So delta is called co-multiplication, epsilon is called co-unit, and S is called antipode. Now, where do the axioms come from and what are they good for? Well, they're good for this thing, and they come from this thing. So, given Voronovich algebra, we can think of it as being the functions of a compact quantum group. At the same time, it's the sister algebra over a discrete quantum group. And these quantum groups are in a kind of Pontryagin duality. So in order to understand all this, let's look at the basic examples. So the basic examples are the functions on compact Lie groups. And on the other hand, the sister algebra of functions on finitely generated discrete groups. So let's try to understand this first. So given a compact Lie group, we take C of G with the coordinates. Okay, so the algebra is C of G, and these coordinates are just functions. They belong to C of G. So now let's go back to the axiom and understand what's going on. So A is C of G, Uij are the coordinates. Of course, it's unitary, right? The entries generate A by Stone-Weierstrass because this function separates the points of your group, right? If two matrices are different, some entries must be different. And now what are delta epsilon S? Well, these are just the transposes of the multiplication units and inverse maps. So if the multiplication goes from G cross G to G, so the transpose should go from C of G, that we call A now, to C cross G, C of G cross G, which is a tensor A. So the transpose of the multiplication is amorphous like this. A goes to a tensor A. Now as the formula of the multiplication is UVIJ is sum over K of UIK BKJ. The transpose is exactly the same formula, you just put a tensor there in the middle. Exactly the thing here, UIJ goes to UIK, tensor UKJ. Okay, so delta is really the transpose of the multiplication. The same for epsilon and s. I mean, these are the transposes of the unit map and the inverse map. Okay. So that's why in general we call such a beast, such an algebra A, we say that it's C of G with G compact only group. I mean, because in the commutative case, it's exactly this. Now, the other example is with discrete groups. It's a dual example. So if you take a discrete group, let's take C star of gamma with the diagonal matrix formed by the generators. So once again, let's go back to the axioms. The generators are unitary, so all the group elements are unitary in the group algebra, so it's unitary. And it is, of course, generate A. Now, delta, if I want to construct it, this U is diagonal now. So here I can put GI. So here I want just to have J tensor GI. So delta should be given by G goes to G tensor G. And that, of course, exists because that's a representation of the group. Okay, so yeah, that's it. It's a unitary group representation if you want. So yeah, it exists. And same for epsilon, that's the formula that you need. And S is just the inverse. So all these things exist. The remark that as you see, it's not really a morphism. This is an anti-morphism. So that's why in the axioms here you have to put the opposite algebra. Okay. So for groups it doesn't matter. When the algebra is commutative, it's the same thing. But for group duals, you need to put the opposite there for things to work. So these are the basic examples. Now, well, we can prove that in the commutative case, actually, it's exactly the C of G's that you get with G compact G group. In the so-called co-commutative case, but no, let's not get in all details. These are C star gamma. So yeah, everything is just fine. I mean, that's at the same time, we have the definition of compact quantum groups in the Lie case, I mean the matrix case, and of the discrete quantum groups in the finitely generated case. And you have a kind of Poincare type duality. Everything is just fine. So that's the basic theory. Now, in interest, what interesting for us is to liberate these guys here, Hn, Kn, On, Un, and you can do it. So why? Once again, let's go back to the axioms. Well, let's take the simplest to take the orthogonal group, let's say. So C of On is a commutative C star algebra generated by these coordinates Uij. And what you know about the coordinates is that they are self-adjoint, I mean they are real, and the matrix that they form is orthogonal. I mean the inverse is the transpose. So in general you do the same thing, but you remove the assumption that the coordinates commute. So if you want to define On plus, the free unitary quantum group, orthogonal, you just need to take the universal C star algebra generated by n square variables, which form a unitary matrix, which is entities are self-adjoint, and the inverse is the transpose. And that's it. And you can check these things here. That's something that was done by Suzuan long ago. They exist, I mean, no problem. So that's your quantum group, On plus. Same for Un plus, and same for these reflection things you can work out. So it's, I mean, the point is that this formalism is so simple. You don't need any kind of algebra or roots or whatever other things used in any other quantum group formalism or von Neumann algebras or Hilbert spaces, or it's just nothing. I mean, any construction works basically. Star algebras with generators and relations. So it's very simple. So that's why I can basically liberate everything. Well, a bit of work. So I have all these guys here, and now the problem is, so we have a big advance now on our program, this cube which was appearing all the time. In the last lecture, now we kind of know what to do with it. So we want to compute the laws of characters for all these guys, and prove that we get the main limiting theorem, free probability. Now, for computing laws of characters, well, we need a lot of theory, like hard measure, of course, yeah. The laws are with respect to the uniform measures. We need to talk about that first, hard, and then Peter Weil's theory of that. So let's do this slowly. So in general, yeah, we have a hard integration that's resolved by Voronovich. Hard integration means something which is left-right invariant. That's the formula. The construction is by starting with the arbitrary linear form and making it a zero limit with respect to convolution. It's exactly as in the classical case. You want to construct a measure, show that any abstract compact group has a hard measure. Take any probability measure and convolve it with itself. And the more you convolve, the more it become invariants left and right. But you cannot just take the plane limit. You have to take this as zero limit for some technical reasons. So now in the general case, it's the same. So examples, of course, for usual groups, that's usual uniform integration. For group duals, now that's something very simple. So the integral of a group element, these guys span everything. So it's enough to specify integral group elements is just this Kronecker symbol. 0 if G is 1, 1. No, 1 if G is 1, 0 out of this. So yeah, this is very simple. Now this once you have our integration can develop Peter-Weyl theory. So let's call co-representation of Voronowicz algebra or representation of the associated quantum group. You always put a co in order to differentiate between like the distinction between A and G. Is a unitary matrix satisfying exactly the same condition as U? So remember, maybe let's go back to the axiom. So you see these three things are exactly these three things here. Okay, but now for an arbitrary unitary matrix V. Example, of course, U, right, from the axioms, and that's the fundamental representation. Also U bar, if you put bars everywhere, which means stars in practice here, then the conditions will still hold true. So any representation has a contragradient, complex conjugate if you want. Now as the theory, of course you can talk about irreducibles, all that home spaces. It's exactly the same definitions as in the classical case. Now the theorem is that, well, the Peter-Weyl theory holds. So Peter-Weyl theory is something somehow big many statements, but these are the four main statements. So any co-representation decomposes as a sum of irreducibles. That's one thing. Then, if you want to compute these irreducibles, you just have to take the tensor powers of the fundamental one, U. Actually, the tensor powers, but with k-color integer as usual. So it's actually the tensor products between mu and U bar, and decompose this. Now, third thing is that once you have your irreducibles, these have coefficient spaces, which are as vector spaces, just some matrices, okay? HR is the space of R, it's finite dimensional. And A decomposes as a direct sum of these coefficient spaces, and the direct sum is orthogonal with respect to the integration, the scalar product coming from integration. So this is of course not an algebra isomorphism. I mean, if you take an usually group where A is commutative, this cannot be a sum of matrix algebras, right? It's a co-algebra isomorphism. I mean, the main part is that it's a vector space isomorphism, but it's actually a star co-algebra if you want to be more precise. And finally, the character of irreducibles form an orthonormal basis of A central. So A central, these are some of the central functions in a quantum group. It's exactly the elements which are whose delta is invariant under the flip. So you can define that, fits with the classical case, and that's the result about characters. Now, well, we want to integrate characters and Truncated characters. So how to apply all this? So you see Peter-Weyl tells you have here orthogonality and here too, but it doesn't really tell you exactly how to compute the integration. So as a consequence of Peter-Weyl, we have these integration results. So first of all, for any co-representation, these integrals, if you want to compute them, just put them together they form a matrix, and that's exactly the projection to the fixed points. That's part of Peter-Weyl somehow follows from what I said before. That's one thing. Now, if you have this, well, you can apply it, of course, to any tensor power of U, right? So tensor power of U to the k with k color integer, it's always color integer. So white corresponds to doing nothing, and black to put a star here if you want. So these are the coefficients of UK, and they span everything. I mean, if you compute the integrals of this, you're done. You have computed all the integrals over G. So if you want to compute these guys, what to do? Well, you use this. I mean, you just have to compute the projection onto fixed points of UK. So for that, let's take a basis. Assume that UK we were able somehow to compute a basis of its decay. Because once you have that basis, so you have to you have the basis, you have to find the orthogonal projection onto the span of that basis. And well, everything depends on the gram matrix on the basis, and actually not on gram, on the inverse of gram, on the so-called Weingarten matrix. It's a simple linear algebra lemma. So here's the formula. So assuming that UK has a basis dk, you take the gram matrix of the basis, you invert it, and then it's a sum of these guys here with those coefficients. It's exactly the basis coefficients of the elements in D. So the proof I already told you, it's some linear algebra to be done there. So this is basically comes from this, but it's in a more concrete form. And this is somehow the Weingarten formula, but in abstract form. I mean, CDK is just an abstract basis of X of UK. So this comes right from Peter Weil's theory. Now in practice, when you see this, well, the problem is to compute the basis of X UK, right? For all these quantum groups you're interested in, so how to compute that. And for that, we need, well, some more theories. We need Tanakian duality. So we're interested in fixed points of UK. And it's actually better to enlarge a bit the attention to all the home spaces between UK and UL. Because it's not such a big deal. I mean, these things depend on two parameters instead of one. But actually, by Frobenius, these guys are isomorphic to home of U tensor KL somehow. So it's basically the same spaces, but just with some multiplicities. And these things are much better than just the fixed spaces because they form a category. You can compose them, you see. Also tensor them, all that. So it's much better to work with this than with the fixed spaces. And Tanakian duality says that such beasts are in correspondence actually with Voronowicz algebras. So let's see how it works. So the Tanakian category of Voronowicz algebra is this thing here, the one that we're interested in for very concrete reasons, I remind you, for computing the higher integral, not to compute these things. On the other hand, given such an abstract thing, Mutsui-Tabula axiom, so-called Tanakian category, we can define a Voronowicz algebra, just take the universal one. I mean, the universalist algebra generated by variables Uij, and impose all these conditions. For any t here, you assume that t is really an intertwiner of U. So you model out by all these relations. These are so-called Hopf-type, if you want, to get into the Voronowicz algebra. And Tanakian duality says that these guys are in correspondence. So this is very good for us because somehow for all the quantum groups we're interested in, like free Yn, free Yn, free Hn, all that. Now somehow you have to compute Tanakian categories the same as that, and that's the Brouwer theorem in the classical case. Finally, what we want are free Brouwer theorems. So let's get now into this Brouwer business. So this is what was done by Brouwer in the 40s. Now it's called Easiness. That's the modern term for all this. So let's do it in general for quantum group. So quantum group is called easy when the tensor category, that's it, the Tanakian category, appears in the simplest possible way. It's spanned by partitions. So what do I mean by this? You see any partition associated with any partition is this linear map. So E1En is the standard basis of Cn. So I plug a tensor here, and what's the coefficient of the output tensor here? I just took my indices on the partition. So pi is a partition between k upper point and l lower point. So I put my indices there. And I look at the blocks of pi. So if the indices fit in the sense that each block contains equal indices, the coefficient is 1. The coefficient here is 1. If something fails there for some block, it's 0. So these are Kronecker symbols. I'm just kind of generalized Kronecker symbols. Anytime you have a picture, indices, you put indices on the picture, and you get 0 or 1, depending on whether indices fit or not. So it's very simple. And so G is called easy when the tensor category appears in the simplest possible way, spanned by partition. And Brouwer's theorem says exactly that Yn is easy coming from all pairings, and also Un is easy coming from all matching pairings. So this is the so-called Brouwer algebra, what I'm doing here. But it works, of course, for any quantum group. I mean, there's no need to assume that the groups are classical. Now, in connection with our examples, so we have how many? 8 examples, 4 classical, 4 free, and Brouwer from the 40s tells you that 2 of them are free. Well, no surprise now, they're all free. And here are the partitions. So this phase here is the continuous phase. We have Brouwer. These are the Brouwer results. Free Brouwer, what happens is that the passage to freeze by removing the commutativity with the coordinates, right? AB is BA, you don't want that. But AB is BA means exactly that the crossing is in the category. So you remove that crossing. So finally, for getting free Brouwer, you take the usual Brouwer and remove the crossings from everything here. So you get no crossing pairings, no crossing matching pairings. For the reflection groups, well, it's a similar business. I mean, you can work first the classical case, that's more or less Brouwer also for reflection groups if you want. These are partitions with even blocks. These are matching partitions with even blocks. When liberating, same as in the continuous case, you remove the crossing, you get the non-crossing versions here. So now, what's to be done? We want to compute laws of characters. So let's first upgrade. Remember we had the kind of Weingarten formula before. Let's take a look back at it in general. Here it is, okay? The linear algebra thing. Now let's see what happens in the easy case. So when this theoretical basis comes from partition, so we'll get exactly the same formula, but these deltas will be now Kronecker symbols, these Kronecker symbols we're talking about. And W will be the inverse of the gram matrix. So let's look at these vectors. What's the gram matrix of these vectors? Well, you compute it, you basically have to superpose. If you compute gram of TP, T pi, and T sigma, you get a sum there, you have to superpose pi and sigma and count the blocks. That's all. So here's your formula. For any group coming from a category, these arbitrary integrals are this kind of Weingarten sums, where decay the basis is now the partitions with the empty set. I mean, they're just you don't have upper legs, just lower legs. Delta are the usual Kronecker symbols we're talking about in the previous slides. I mean, here these are these Kroneckers. And the Weingarten matrix in the inverse of the gram, and gram, if you compute it, that's it. It's very simple. You superpose pi and sigma as the joint, count the number of blocks, and it's n power of that. So this is very nice, and of course it's a generalization of the Weingarten formula already talked about in the first lectures. There are also twisted superversions of it. I mean, it also covers the symplectic group. That's originally this was done by Colin did these things for ONUN and SPN in a very clean way, and then by me and Benoit and other guys in from the corner group case. So that's your formula. So now, well, I guess we have everything. It's just enough to plug into this thing, these categories here, and we'll get the law of characters. So, well, let's stay first at the abstract level. So given an easy quantum group coming from a category of partitions, if you want to compute the moments of the main character asymptotically, well, you have to count the diagrams here, right? Because these are exactly the number of fixed point spaces of UK. That's bound by partitions. So these partitions are not exactly linearly independent. When it's small, what would then big, they become linearly independent. So the dimension of the span is just the number of elements. That's it. You don't even need Weingarten. This follows from Peter Weil. That's all. For the truncated characters, no, it doesn't work just from Peter Weil. We need Weingarten and everything. And here you get this formula here. Any partition will contribute to the no longer one, to the truncated one, which is t to the number of blocks. So now we're ready into this to plug these 8 categories here. So I have the formulas. It's enough to plug in these 8 things here and get the laws. And no surprise, we get, of course, the laws. That's something that we more or less know. The 8 main laws in free probabilities here, which I remind you are normal, complex normal, Wigner semicircle, Voiculescu circular. These are the Bessel laws. More precise, real Bessel, complex Bessel, free real Bessel, free complex Bessel. So very good, we're done with this cube. I mean, we'll be having the cube for some time, and yeah, that's it. So cube comes from the basic quantum groups. It's just a law of truncated characters. The basic quantum groups, let's go back to them. So many cubes here. Yeah, here they are. It's really beautiful, this diagram, because you have inclusions here, and also it's true that not trivial at all, and actually not fully checked that you take any face here, the quantum generated by the middle object is the big one, things like that. I mean, there's a lot and a lot of structure here, which is not that that clear in free probability. I mean, for the measures, in free probability, the only thing here are the correspondences between up and down. There's Berkovich pattern, but here you have much more structure. It's really more beautiful and also better than things like subfactors or noncommutative geometry. So that's the good, the most powerful cube. There are many cubes, but this is the most powerful cube. This thing here. So we're done with this. So yeah, these are the laws. Now, in view of this, so these Bessel beasts are really extremely important. I mean, there are 4 of them. Half of the main measures in probability are Bessel, right? So let's go to them and try to understand a bit what's going on. Full details. So first of all, I remind you, so this will be a mixture of things that we've seen already, but more details and also a few new things. So first of all, definition is come by making a compound Poisson limiting theorem with a variable t, as usual, truncation variable, and the measure that you plug in is the uniform measure on the S roots of unity. Now, what are the main examples? At S is 1, let's go back here. So what happens when S is 1? Well, uniform measure on the first, that's just 1. So you put in delta 1 here. So if you put delta 1, of course, here it gets Poisson of t, here Poisson of t. Okay, so at S is 1, the limiting result is just the PLT. You get PT and pi t. Now, S is 2 here things become interesting. So here we obtain the so-called real Bessel law. By the name, because all the others are complex. I mean, roots of unity of order 2 are plus minus 1, but the others, they start to be complex measures. So that's the real measure. I mean, this is 1 also, these are real, but they are not true Bessels. So this is called real Bessel. And of course, it's supported by Z, right? Remember, these are characters, let's say, of the hyperoctahedral group. So yeah, it's supported by Z, and the density is given by this weird function here, which is not very weird. I mean, it's the Bessel function of the first kind, if you ask people around. So it's something well known in analysis. So that's why we call this Bessel laws. So yeah, thesis to the classical law is the Bessel law. And well, in general, we get a kind of fragilization of this, which is also called Fuchs-Catalan law. I mean, so factors theories things are kind of known too. They call them Fuchs-Catalan there. We'll be back to factors in a minute. The other case we're interested in is S is infinity. This is a somehow purely complex case. So here, according to our philosophy, yeah, we'll denote the complexifications of these capitals. It will be capital T and capital supposed to be Greek, but it's Gothic because Greek doesn't exist. Okay, so this is the definition, main examples. Now theory. So that's the first thing about compound Poisson laws. This can define alternatively as sums of certain variables. So here's the results in this Bessel law case. So these are just the laws of sum of variables which are Poisson of t independent, or free Poisson of t free in the free case, as sums weighted by roots of unity. Okay, that's something we've seen more or less last time. And the proof uses this thing, which is also a theorem. So if you want to compute Fourier transforms, either starting from the compound Poisson limiting theorem or from this thing here, well, you get the same thing. So that's the proof that the definitions coincide. And that's the formula for Fourier. And that's the Fourier of Bessel. And that's their transform of free Bessel, this beast here. So this, well, these Bessel laws, they're kind of terrible. If you want to compute the density, for instance, you see, let's go here. At S2, that's the density, but at S3 is just something terrible in the complex prime. I mean, it's very hard combinatorics, but this is somehow best offer. I'm selected here in the 6th slide, so everything looks very simple. So yeah, very simple, very simple to, and this formula is already very simple, but if you want to get beyond this, it's really tricky. I mean, it's just terrible combinatorics and also analysis, complex analysis, and many things. So apparently we have 2 more slides with simple things. Let's see what's inside. So first, yeah, that's something that we know, the formal convolution semigroup in a classical case, free convolution semigroup in a free case, and we have Berkovich-Pata bijection. So I semigroup, you see my T is just here. So I remind you log F linearizes the convolution. So if you take log F, it disappears, so it's linear in T. So it's just fine, it's a semigroup. The same for R here. T appears here, so it's not in this sum, so it's a semigroup. And we have Berkovich-Pata. Finally, one more thing. There are many multiplicative properties now with respect to free multiplicative convolution, which are very interesting, but we don't really have time here to get into all this. So I refer to my paper with Belinsky, Kapitan Collins. It's called Free Bessel Law. So very easy to find, and there we work out all this and other things. So let me just tell you the main results that I haven't talked about yet here. So this appears as a free comparisons of multiplicative convolutions powers of pi. Pi is the Marchenko pasture of 1, okay? So this means, I mean, yeah, if we take T is 1, I mean, the S Bessel law at 1 is just the multiplicative power of pi, which is very interesting. So that's a very interesting thing. So alternatively, you can write it in this way. I mean, here you have a compression meaning by a projection of trace T. But, if you want something just with the signs here, very abstract, that's your formula. And in particular, you see, I mean, there's a kind of duality between S and T. I mean, that's very weird because S is the parameter, the roots of unity there, and T is the truncation parameter, so they're apparently not related by anything by definition, but they are. So you see, particularly for this formula, so S corresponds somehow to the power of, let's call it box times this thing, that's the latex name, and this is box plus. So S corresponds to box time and T to box plus, which is really weird. I mean, T is the truncation parameter, I remind you, and something technical. And this is the order of roots of unities. They have nothing to do, but actually they have. I mean, you can see here, all these formulas are very beautiful. So very nice, all this. Now, well, let's go to some questions now. So we learned so many things now. Somehow we've seen that free probability on quantum groups and classical groups, yeah, everything quantum groups, it's the same thing, okay? Now let's try to get a bit beyond that, to look at other things like factors, noncommutative geometry, and also a bit more questions about quantum groups. So I start with classical groups. So, well, first of all, as a general quantum group thing, so we know that this appears as asymptotic laws for the reflection groups and their free versions. Now, in the classical case, these are not the only reflection groups. So the story is that the complex reflection groups, they were classified in the, what was that, 70s maybe. So it's a series and then exceptional examples. And the series is exactly this with one more parameter added. So that's the series, the general series of complex reflection groups. You take these things here. So this, I remind you, are if you want permutation matrices with instead of one entries, you put roots of unity over the rest. And in addition, you can ask for the determinant to be 1 or a power, the d's power of the determinant to be 1. That's your extra parameter, the d. So that's the series of reflection groups. And then there are some exceptional examples, but won't bother with them. Because anyway, we do things asymptotically, we is already here. So we cannot do our things probabilistic and the exceptional things. So this is the series. Now, well, if you have this condition, nothing much will change. I mean, you basically get the same asymptotic laws, but the fluctuations are to be understood. So there are some technical questions here. And I don't think these are known because people in group theory, I don't know, many of them, unless they do quantum groups or a bit physicists, they are not very interested in this probabilistic things. They are wrong, of course, completely wrong. But these are things to be done here. Now, in the free case, Well, in the free case, there are actually many examples. It's not the same situation as in the classical case. So there are many, many series, even infinite families of complex reflection groups. So let's start with the real case. So things between, so if you want hyperoctahedral quantum groups, these were classified by Rome and Weber in the easy case. So there is a series and a family which is uncountable depending on a discrete group, the central assumptions, and then a series. So it's really very big. Now, in the purely complex case, meaning between Kn and Kn plus, this is not known, but it's expected somehow to be a situation to be a complexification of this. In general, the big problem is to classify everything between Hn and Kn plus. It's a tough question. So, Weber and the guys there in Saarbrücken are working for classifying things between On and Un plus. And that's a simpler question. So, I think that question is still extremely difficult, and this is even more difficult. So that's the classification of quantum reflection groups. Very good problem. And that's algebraic. In addition, I have to the question of compute understand the laws of characters, see how they fit into free probability, somehow develop more free probability in order to make these things fit. So there's a lot of work here, and analytically, even for these Rome-Weber things are not really fully known. A lot of work here, definitely. Now, what else can we do? Noncommutative geometry. So let's go back to the main examples of quantum groups. That's the same cube that we're using all the time. This somehow corresponds to the four main geometries, right? I mean, we have the real geometry, HN-ON, right? ON is the continuous group, HN is the relevant discrete group. Then the complex geometry with KN-UN, then the free real one and free complex one. In Java, you can axiomatize some noncommutative geometries, but you also need a sphere in the torus. It's a bit more complicated, but it basically comes down to this quantum groups, a discrete one and continuous one. So classification problem, well, under more assumptions, and there are classification results, but all this is very related to this Braun-Weber and other Star-Argo-Mang classification work. So this kind of problem has a non-commutative geometry version, which is a bit different. I mean, it's not exactly the same thing, but it's very related. So once again, such questions. Now you mentioned non-commutative geometry. Let's look at the tori. That's very important. So the tori of these geometries, in the real case, you get the same torus for the orthogonal and hyperoctahedral group, and same in complex, and actually same in free. So the torus is unique. And here are your tori. So here you get the cube actually. The discrete torus is a cube. Here you get the usual torus, one-dimensional. And the liberations, well, if I want to liberate this, the tori are group duals. So it's better to view this as the dual of itself. In order to liberate it, just take a free power of Z2 instead of usual power. So I get this. The same in the complex case. This is the dual of Z to the n. So if I take a free power of Z now, that's your free group. So these are the tori. Now the problem is that, remember, let's go back to the cube. Here the vertical, so the liberation operation probabilistically when you look at characters is Berkovich-Pata. For the tori, these things are well known. It's Meixner, free Meixner. It's not exactly Berkovich-Pata. So the problem here is somehow it's half free probability question, half non-commutative geometry question. But quantum groups, of course, everywhere around too is not unifying somehow Berkovich-Pata and Meixner, free Meixner, because we'd like to understand what's a free manifold, how the manifolds liberate, and probabilistically some like these ones here on the bottom liberates according to Berkovich-Pata, but the tori liberate according to Meixner, free Meixner. So how to do this? And this, of course, n is big in everything. So very, very difficult to formulate something precise, but that's the problem. There are two things: Berkovich-Pata, Meixner, free Meixner. How to unify them? No. One more thing and we're done. Yeah, a lot of mathematics here. Let's talk about subfactors. That's something that we haven't done yet. So associated to a finite index subfactor, well, you can construct the John Tower, planar algebra, and then a spectral measure. The subfactor is the one having as dimensions these things. Of course, there are relations of quantum groups, so that we won't get into details, but that's the measure. I mean, when the subfactor comes from quantum group, that's the law of the character. Now, for temporary leap, we get Marchenko Pastur, free Poisson laws. For Fuscatan subfactors, which are, there is a hierarchy there in subfactor 2. So temporary leap is level 1, Fuscatan is level 2. Well, we get free Bessel's laws, exactly the same hierarchy as in quantum groups or probability. Marchenko Pastur, free Bessel. Now, the problem why is that subfactor is not clear what's the meaning of T of the truncation parameters. In quantum groups, we know, because you have a concrete variable there that we can truncate. Here you have no concrete variables, it's a variable. There's no integral there, it's not clear what's the T, so that's no problem, what's T. And finally, but this is really terribly technical, in index less than 4, Jones has this, well, Jones hasn't done this manipulation on Poincare series, but he calls the theta series. It's something very tricky, factor-ish, which produces, well, theta must have positive coefficients. That's a factor abstraction. And with Dietmar Bisch, we had some fun looking at what happens when doing this manipulation by the level of measures. So you do exactly the same thing. I'm going to take the measure, having as still just transform this theta if you want. And that leaves on the unit circle. So it blows, this transformation blows up mu, which is supported by R, onto the unit circle, and the formula is extremely, extremely simple. It's less than 4. So the problem is what to do in general, and yeah, that's related to physics, all that. And Evans and Pugh works on that, and also me and Dietmar. And yeah, it's also related to this T, yeah, to everything. Okay, so that's pretty much it. We have seen that, yeah, free Bessel are central objects. Once again, it's level 2. Level 1 is somehow, say, circular Marchenko Pastur, all that, and level 2 is free Bessel. And that's the free probability on groups of factors of geometry. So, yeah, the current level of research is right above a bit free Bessel. So, next lecture, random matrices. So that's something we haven't talked about yet, and well, just a bit of it in various lectures. So, we'll try to understand what's the relation between these free Bessel things with random matrices, and generally how random matrices fit into this philosophy I was telling you, level 1, level 2, and so on. So that's for the next time. See you soon.